This is going to be my recording of a compute shader project that I've completed for my advanced graphics course as part of my graduate studies. And for this project, we had to implement a compute shader of some kind for to get experience with compute shaders. And I did this project in Vulkan, and I implemented a compute shader using Simplex noise, which is able to calculate HSV values and or randomly generate HSV values and displace a grid with these values. And this is what it ends up looking like. The purple areas are higher than the red areas. My lighting equations don't apply to this because I don't calculate normals, but for this demonstration purposes, we can see that the heights are being displaced. But the actual cool part of this is that simplex noise is permutable, and it is somewhat stable when you permute it. So it actually looks pretty smooth when you do that. So if I go ahead and permute this, and I had this set up for a different frame rate, let me change this real quick. If I slow this down, go ahead and rerun this. Okay, so we're back here, and if I go ahead and permute this again by hitting P and then the up arrow, you can see that it kind of animates around as the permutation values are changed. And I can permute it up and down with the up and down arrows, and it does jump every now and again. And I believe that's because we're jumping locations within the underlying grid that simplex noise is built off of, and I can actually demonstrate that. If I permute, I can change the underlying X and Y resolutions of the underlying noise function. But if I change Y without changing X, it'll just scale it. If I scale this down, this is actually much easier to do if I actually make the grid smaller. So if I make this a scale of 1, and I go ahead and speed this back up, but the underlying grid is just it's created by a scaling a dimensional size. So there's 32 vertices by 32 vertices, and then multiplied by whatever scalar I give it. So if I give it a smaller scalar, it has much fewer vertices to work with, so it looks a lot blockier. And the permutations are also a lot faster because the I didn't tweak the acceleration value for the higher frame rate because it does run a lot faster when there are fewer vertices. But if I go ahead and change our Y scale, and I go ahead and scale it in, that's getting bigger. But if I scale out all the way, you can see that it kind of devolves into these repeating ridges and grids. And that's because the underlying mathematics behind simplex noise is built off of almost like a repeating diamond pattern in a grid. So you can kind of see the edges of that here. If this was a higher resolution, we would be able to see it a lot better. But this kind of gets that point across. And to kind of show how this is working under the hood, because there is some improvements that I would like to make here. If I go ahead and open up Insight Graphics, and this runs the debug version, so it takes a little bit longer to load. And I'm using a different version of the API than what using some calls from a newer version of the API, and I forgot to change the API version. And there's also something about descriptors in here, which is odd because my normal debug mode doesn't catch that, but I know NVIDIA injects their own validation shader, layers here, but we'll ignore those for the time being. So for demonstration purposes, if I go ahead and capture that and I go to my vertex shader, you can already kind of see how dense this grid is and with the number of indices that it has, but we'll go ahead and open the model itself. Or maybe we won't, because NVIDIA Insight will just crash on us. That's okay too. Or maybe we will not. Okay. That is crazy. But if we go ahead and open this, rotate this. If we zoom in, we have to zoom in quite a bit before we can actually see the individual vertices. So this grid is really big, and that is what causes a lot of this slow down, or like the lower frame rate that I see with this. Actually, if we profile these shaders, what's actually cool about the way I implemented shaders is that I use an online shader compilation process. And with the compiler that I have, with the library that calls the compiler, I can give it an argument to create debug values within the shaders, and that lets me get actual like additional information about what is slowing down shaders and stuff like that. So what we can actually see is the vertex shader spends most of its time waiting, and that's because it's waiting on the compute shader to finish. And this other LGSB, I believe, is from actually having to copy over all the vertices, because this model's huge, so I'm imagining that there's probably some underlying operation that's taking a little while to copy over that information. But I might have to look into this more, because I don't quite understand what a scoreboard dependency is. But anyway, it could be either the compute shader or I believe that's the copy, but that wait for sure is from having to wait for the compute shader to finish. But anyway, if we go ahead and close that and run this one more time. Yeah, this is my compute shader project. And I didn't change the acceleration value, but by default, if you decide to run this, I will have set it a lot slower, or I will make it so that you can change the acceleration value by hitting the A key, which is not a thing right now, but will be if you check out my GitHub repo, which will be in the description. Anyway, thanks for watching.